Okay, let's begin. I sent an email message yesterday to resident students and distance learning students. If you did not get a message from me, send me an email message. If you did not get an email message from me, did everyone here get it? Or we have a new student?
Professor, I just got added last.
Yeah, so you're
no
problem.
Talk to you about it after.
No problem. I've added you to my distribution list.
Okay.
So, did everyone receive that message? If you did not, you need to tell me, okay? And this is especially true for the distance learning students. Okay. All right. So, incidentally, normally we would have a problem session this week, but it's a short week and we've got to do the first experiment because of Jay's travel schedule. So there's no problem session this week. You'll notice that in the syllabus, right? Yeah. Okay. Any quick general questions before we get started?
Somebody's on.
That just means they're on there. Okay. All right. So we're talking about the standard oscillator. It's a one-dimensional motion of a mass on a spring here. The spring is anchored over here. This is an ideal case. The spring has no mass. Right? All the mass is here. There's no friction, no air drag. We'll put dissipate effects in later. Right now we just want to look at the simplest case. So this is really the simplest kind of oscillator. And the spring obeys Hooke's law. The force that it exerts is opposite the direction. You stretch it or compress it, and it's proportional to the distance. And from this, we find the differential equation of motion for the coordinate here, x, where x equals 0 is equilibrium. This is the differential equation that x satisfies. And there's one parameter here. It's we call it omega naught. It's the square root of the spring constant divided by the mass. And we know what this, from this perspective, this is just a parameter of our system, but we know what the meaning it has is, right? When this oscillator is oscillating, it has a certain frequency. It undergoes so many cycles per second, right? A cycle per second is a hertz. Well, omega naught is not, that's F naught, okay? But omega naught is the frequency, the number of cycles per second, times 2 pi. And the 2 pi is in there because in one oscillation corresponds to 2 pi radians, right? Now, if you're a little confused right now, I don't blame you, because we're talking about motion like this, and it sounds like I'm talking about motion in a circle, where there's an intimate connection that we're going to talk about today. But for right now, to appreciate these quantities here that we need to deal with, this is obvious. The period is the time it takes for one oscillation, right? And the reciprocal of the period is the frequency. This is 2 pi. You can see it from here. Omega naught is 2 pi. So you want to think, and again, we're going to go through this in depth today, but I might as well tell you right now, when something's going around in uniform circular motion here, all right, it has a certain frequency. It'll do so many cycles, so many revolutions per second, right? What's the angular frequency, which we're calling omega naught? It's the number of radians per second. And there are 2 pi radians in a circle, right? You know this. Let me write it down. There are 2 pi radians in 360 degrees. So the way people think of this is we divide by 2. Here's your, this is how you convert between the two, okay? So that's the meaning of this omega naught. It's the number of radians per second. And to appreciate it, instead of thinking of this, you want to think of this. And there is a connection, as we will see. A hallmark of this linear motion here of Hooke's law is that the amplitude, the frequency, is independent of amplitude. And a lot of people just take that for granted, but it's really remarkable. And it really simplifies things. And we're going to be this whole, I don't think I told you this yesterday, you know, this whole course is going to be linear acoustics or linear vibrations and oscillations. We're not going to, I will occasionally mention nonlinear effects, but in acoustics you can get away with linear theory, that's what we're doing here. you can do a lot of acoustics, but eventually you're going to hit problems, right? Shock waves are a standard example. That's an inherently nonlinear wave. Okay, so the next thing to do here is we've got this solution. We notice there's two solutions here, and for a linear differential equation, if you have two solutions, the sum or the difference or any linear superposition is going to also be a solution. So we have a solution here, and the claim is that that's the general solution. Any motion of our oscillator can be described by this equation. So how do we prove that? Well, it's a simple way to do it, and also going along with that is that we need to be able to do this. We need to be able to uniquely specify motion. Often we don't care, okay? We just need to know a type of motion that's going on. We don't need to come up with a unique specification. But it's appropriate to do that here and to show that we can do it. So what do I mean by uniquely specify the motion? Well, let's give our oscillators specific initial conditions. Let's imagine that at time t is equal to 0, I've pulled this thing over here, or I've pushed it in a certain distance, and I've given it some arbitrary distance, and I give it some arbitrary initial velocity. Okay, so those are arbitrary initial conditions. They can be anything. Now, okay, I have to say that that's really not true, because if you really had an oscillator here, can you just pull this aside any amount of distance and let it go? And you can try, but what's going to happen if you pull it too far? You're going to overstretch. You're going to change the spring. You're going to change the equilibrium. So these are realistic effects, right? They're not in our model. What if I push it in? Can I push it in as far as I want to release it from rest? What happens if I push it in too far? The turns touch. Now you have a rod. It's also actually described by Hooke's law, but the stiffness is much greater, right? So the system becomes nonlinear. Everything becomes nonlinear eventually. What's remarkable in acoustics is that we can get away with linear theory for a lot of phenomena. A lot of, the sound from my voice is remarkably small amplitude. You would be amazed. We'll talk about that next quarter. Okay, so there is an assumption here. When I say that we're going to give it any initial conditions, that's ideally, we're not worried about these realistic effects. That if you pull it too far, you're going to exceed the elastic limit of the spring, or if the turns touch, all of a sudden the spring constant jumps up by a factor of, I don't know what it is, typically. It could easily be a factor of 1,000. It might be 1,000,000. I don't know, I've never quantified that. Okay, so here we go. This is not right. How about there? That's better. Okay, so these are arbitrary initial conditions. Initial position, displacement from equilibrium, and initial velocity. Here's what we claim to be our general solution. I need to differentiate it with respect to time because we're going to impose these two conditions. All right, so this we talked about. This is simple differentiation. I don't think anybody has a problem with that. Some of you may need to refresh your memory about this, but this will come back to you, I'm sure. So at time t is equal to 0, we demand that this equals x0, something that's specified here. So this is x0. What's cosine of 0? 1. Right? What's the sine of 0? So we conclude we have to set this arbitrary constant in our solution to the differential equation. We've got to set it equal to x0. No problem, we can do that. What about the velocity? At time t is equal to 0, this is not here, the cosine of 0 is 1. We need to set this equal to u0. So that means this amplitude A2 here has to be u0 over omega naught. Right? I can solve for that A2. Again, that was an arbitrary constant in our solution to our differential equation. So here's the solution. So what we've done here is we've found given some specific initial conditions, no matter what they are, this is going to be the solution. This proves that this really is the general solution because it can handle any motion, it can handle any initial conditions. That means it's got to be the general solution. It can handle arbitrary motion of the system. So that proves that it is the general solution. specific solution. Now, often we won't go this far, but it's just sometimes good to see this stuff, okay? Let's look at our alternative solution. Remember this yesterday? Instead of the sum of a sine and a cosine, an equivalent solution is to just take cosine or sine, it doesn't matter what's here, but you put this phase here. So again, we have two arbitrary constants. Is that a general solution? Is that one form of the general solution? Well, let's see if we can impose these general boundary conditions and get it to work. So at time t is equal to 0, this has to be x0. So I get this, right? Everybody following me here? The derivative of this is this, time derivative. So at time t is equal to 0, I've got to get u0. So now we need to solve. Here we solved for a1 and a2, and it was really easy, right? Now we've got to solve for a and phi. It's not so easy, but and those of you who took mechanics from me, James, Robert, you're taking the sequence out of order.
Yeah.
So is this your last acoustics course?
Yeah, Ross.
Is that right?
Yeah, right. I'll graduate this tomorrow.
You know, it sometimes happens. It's amazing. So Young has taken all of the acoustic sequence, except the first course. It's welcome to NPS, right? Okay. And Kevin and Michael. So those of you who had mechanics from me know what you know how to do this. The quick way to do it is isolate this cosine. Take the a over here. Isolate the sine. Bring this stuff over there. So I have something equals the cosine, something equals the sine. If I square those two equations and add them together, what happens?
It's 1.
Who said that? Yeah, but you took the mechanics. What about the other people? Maybe you're not, maybe you just can't see that. So the easy way to do this is to write the first equation like this. And the reason I'm going through this is this happens actually quite a lot. We get this, right, and we get minus, where is it? Minus u naught over omega. Oh, what am I doing here? Over omega naught a. Now, I need to find a. I can find a if I square this equation, and add the left-hand sides and the right-hand side. What's the cosine squared plus the sine squared? It's 1. So I've eliminated phi. That's the quick way to do it. And we solve for a. And here it is. Okay? So we've solved for a. The remainder we need to do now is solve, I'm going to erase this, is to solve for phi. How do I eliminate, there are other ways of doing this. This is the quickest way. I shouldn't have erased the, sorry. How do I eliminate a from these equations here? I take the ratio. I take this equation and put it underneath here. So I'm going to put this here and this here. And why am I doing that? What happens to a? It disappears, right? And now I could have taken this divided by that, but I went the other way because that's going to be the tangent, which is more common than the cotangent. So here we find we can solve this for the tangent of phi and eliminate a. So phi has to be the inverse tangent of this. All right, so again, we've shown that this is a general form of the solution because we can handle any initial conditions. Our solution can handle any initial conditions. That means it's the general solution. So we have two forms, as we saw yesterday. And it's often more convenient to use this form, but sometimes it's convenient to use this. But the point at this point in the course, just you want to recognize that we have different forms of the general solution here. So these are equivalent. Okay, let's for definiteness, let's assume the initial velocity is 0. So I have this oscillator. And I'm going to, here it is, I'm going to pull it aside from equilibrium. I'm going to pull it over here and release it from rest. Okay, so U naught is equal to 0. And X naught will be just some amplitude. We'll just call it A. And I release it from rest. What does the motion look like in time? What does our solution look like? We have the solution as a function of time. Well, here's what it looks like. We just get, you can use either form of the solution here, but it's just going to be a pure cosine wave in this case when we pull it and release it from rest. What's the slope here of this? See this solid curve here? That's a cosine, supposed to be a cosine. What's the slope here?
0.
Yeah, why is it 0? Because it's a cosine. Don't say because it's a cosine, that's like cheating. Because the velocity is 0. Remember the time derivative of this is the velocity. So we've got initial velocity equal to 0 here. It's just our initial conditions that we've chosen. So this is going to be a cosine wave. It's going to just, I pull it aside, let's say, over here. This is x equals 0. This is x equals a. And it's just going to oscillate like this. It looks like that. You'll notice here that the velocity is shown with the dashed curve here. See, this is the velocity. The velocity we can get, well, we can get it from, phi will be, for our initial conditions, phi will be 0. So here's the velocity. It's a sine wave, minus with a negative sign. So it's going to look like this, okay? You'll notice the initial velocity is 0, and it's going to go like this. Now, I can't compare these amplitudes here. Why? Why did I draw the dashed line? Why didn't I draw the dashed line bigger? Why didn't I draw it as the same amplitude? Why? This is so simple you probably can't see it. Units, thank you. Who said that? Yeah, they have completely different units. We can't compare. It's comparing apples and oranges. Okay, so you'd have to, if you wanted to actually show this with a scale here, you'd have to have one scale for x and one scale for u. They have different units, so it doesn't. So the amplitude here doesn't matter. What you want to notice here, and students usually have trouble with this in the beginning. Everybody goes through this. When you talk about oscillations and then waves, in the beginning when people study them, they tend to focus on amplitude. They think that's like important. But just as important as amplitude is phase. So that's why I want to point out to you here, to start thinking about phase here. You'll see here's the displacement, here's the position as a function of time. The velocity is not in phase with the position, is it? Is it ahead in phase or behind in phase? Okay, now it looks like it's behind because this peak is behind that, right? But this is time. So as time goes on here, at a point in time here, I hit my velocity peak. Have I hit my position peak? No. So velocity is ahead by 90 degrees here. 180 degrees, if you want to see an example of where's the acceleration? Yeah, so the acceleration is 180 degrees out of phase with the position. You can see that they have the same zero crossings, but when this is a positive maximum, the displacement, the acceleration is negative. So they're 180 degrees out of phase, that's what we say. But the velocity here is halfway in between being right on phase and being 180 degrees. It's 90 degree phase difference, and the velocity leads the displacement because you hit the peak sooner. This is the way I do it. And I do this all the time. As time goes on here, I hit the peak, and then a phase of 90 degrees later, I'm going to hit the peak of the position. So the velocity is leading the position here by 90 degrees. Now don't worry if you don't get this. We're going to see this so many times. Phase is really important, and you'll just naturally get to see this. But I just want to, it's good to introduce it here. Okay, any questions about that? Okay, next is, I said this in the mechanics courses, you guys will remember. Probably the single most important fact in physics is energy conservation. If you think about it, it's probably the most important thing. And what does that mean? It means that if I have some isolated system, okay, no influence from the outside, there's going to be some energy in here. That total amount of energy cannot change. Energy is conserved in an isolated system. It can go from one form to another, but the total amount of energy has to be constant. And that's probably the most, like I said, the most important single fact in physics. So let's look at our system here. Is it isolated? Yeah, we're not driving this from the outside. Right? You might say, well, wait a minute, there's a gravitational force here, but that's being balanced by the normal force. We could be out in space and remove this surface, right? So this is an isolated system, so the energy has to be constant. How many different forms of energy are there here in our system? Well, this mass can have kinetic energy, right? What about the spring? Potential energy, right? Now, real springs have kinetic energy too because they have mass, but we have an ideal spring, right? So because it has no mass, it's purely, it stores potential energy, that's it, there's no kinetic energy. Now, Friday, you're going to be dealing with real springs, okay? They have mass, and you'll see how to handle that in the analysis. There's a way to handle that. But in our model system here, it's very simple. We have kinetic energy here, we have potential energy here, and that's it. If there were friction here, we would have to worry about the thermal energy in the surface. When something slides over a surface and it heats up, you get thermal energy, microscopic kinetic energy. You have to take that into account. We don't have that here. We're in our model. There's no friction. And no damping due to the air, similarly. Okay, so the kinetic energy, most people remember this, it's 1/2 the mass times the square of the velocity, right? What's the potential energy in a spring? Well, I think all of you have had this. Some of you may have forgotten it, but you can show that it's 1/2 the spring constant times x squared. Most people know it as 1/2 kx squared, but we have to use s, right? Because we're going to need that for the wave number. So that's the potential energy. That's elementary mechanics. So the potential energy, we can, to try to see what's going on here, this is a function of x. We can consider things as a function of x here, rather than time, because we have this x here. The potential energy is an upright parabola. Looks like this. What's the potential energy in equilibrium? 0. The spring is neither stretched nor compressed. It's a maximum at the ends here, and incidentally, this is equilibrium, okay? We call these 2 points here turning points of the motion. I should have written that down. That's a nice way to say it, and very common for people to say. We call these turning points. It's where the oscillator, the mass, is turning around. Okay? So it's going out here like this. It's oscillating like this. When it comes out here, at this moment, when it's turning around at the turning point, the velocity is instantaneously 0. So we call those turning points. Potential energy is a maximum at the turning points. What does the kinetic energy have to look like? We know the total energy has to be constant, so there's no choice here. What is it? Evidently, what does it have to be? It has to be the same parabola, but just inverted. So that's what I've sketched here. The kinetic energy has to look like this, because it's the only way I'm going to be able to add this curve to that curve and get a constant. You'll notice the kinetic energy is 0 at the turning points, because the velocity is instantaneously 0. It's a maximum at equilibrium. Well, we can't go any farther here. And this is the way research works. We have to check something. Remember, don't forget, we have a solution. I'm going to use the amplitude phase form here. We have a solution. We need to check that solution, and we can check it with energy conservation. It had better be true when I substitute our solution into here that the sum of these two things is constant. So we need to check that. So let's do it. Here's the total energy. We substitute our solution. So here's x. We're going to use it's better to use just the amplitude phase, just a single sinusoid here. I substitute it in here. 1/2 s times the square of that. You can see that that's there. And then Here's u. U is just the time derivative of that. So it's going to bring out an omega naught squared. Here's 1/2 mu squared. And now stare at that. This has to be a constant. The time has to disappear here. Can you see how's the time going to disappear? It has to be a constant. Well, you got to look at it. Remember what omega naught is? Omega naught squared? It's s over m, right? So when I substitute s over m, the m's cancel. I get 1/2 sa squared, 1/2 s. I can factor the 1/2 sa squared out. I did 2 steps going from here to here, okay? And this is often the way that it is. People, if you wrote down every mathematical step, nobody would want to look at it. This would be too messy, too long. So what have I done here? I've factored out this common factor, and I have, remember what was here? I have the sine squared plus this cosine squared. It's going to be 1, right? So that means this will collapse down just to 1/2 sa squared, which is a constant. Is it the right constant? Well, yeah, because remember at the turning points there's no kinetic energy. We know that the energy then has to be, one form of expression of the energy is going to be 1/2 sa squared, because at the turning points there's no kinetic energy. And x is equal to a. So that's got to be right. That's got to be right. And so people in research do these kinds of checks all the time. You're continually checking yourself because you're doing something nobody's done before, right? That's what research is. And you do it because often it's not right. It happens to me all the time. And you have to go back and find out where you made a mistake. That's research. So here it's very simple. We knew it had to work, but I just wanted to let you know that this is the kind of thing you want to be thinking about. Look for trouble. You know, in research, you got to look for trouble. You might as well start while you're taking classes, right? Because I don't really see much of a difference between teaching and research. To me, they're sort of combined. And when I write journal articles, I've combined the two. Often. Not always, but often. Okay, now we can take this one step further. At equilibrium, the energy is completely kinetic. So that means one expression of the total energy has to be the maximum kinetic energy, which is 1/2 the mass times this u squared. Oh, now we hit something important. In KFCS, everywhere or almost everywhere, a capital letter is going to denote the peak amplitude, an amplitude. Okay, so, and this is a good thing. I like this notation. So it's not a big deal right now, but as we go on, there's going to be more and more notation. And one thing you can almost always count on is when you have a variable, in this case u, the velocity, which is a function of time, the capital letter is going to be used as the amplitude. So that's what we've done right here. Now the next question is, well, okay, but does this equal that? That's the next question. Does that equal that? Well, let's see here. Here's our expression for the velocity. What's the velocity amplitude? Well, it's just, forget the sign, that's irrelevant. It's just going to be omega naught a. So the velocity amplitude evidently is omega naught times the displacement amplitude. We get it right from there. If I take this expression and substitute into there, I get this. So it works. Again, though, we have to use the fact that apparently I didn't even write down there. Great. We're using this fact to show this equivalence here. We're using this where the whole thing began, right? So we're using that to go from here to here, like we did up there. Okay, so everything's fine from an energy point of view. And in this course, we'll always come back and look at energy. It's almost always important. Any questions about that? Okay. So, everyone's seen complex numbers, right? complex number has a real part and an imaginary part. That's a whole theory of mathematics. It's called complex analysis, and there's great theorems, and it gets really involved. All we need here, we don't need the complicated stuff. All we need here is just for you to recognize that we're going to see, and some of you know this, that it's extremely convenient to use complex numbers to deal with waves and oscillations. And in fact, you're crazy if you don't use it. It's so convenient. So to motivate that, we're going to develop it for our particular case of this oscillator here. We're going to start with what's called, here's our general solution. Again, we're going to use the amplitude phase form. And we're going to start by introducing, and then we'll remove. It's just a stepping stone. What are called phasors. Have you ever heard of a phasor? They occur in optics. People in optics use them. No one's ever heard of a phasor? Oh, it's not a Star Trek weapon. Isn't that called a phaser?
Stun or kill.
Yeah, stun or kill, right. I guess it was just one or the other. There was no continuum there. Okay, so here's what a phasor is. What it is basically an arrow. You think of this as a rigid arrow. It's a vector. Rigid arrow has length A, and it's going. I erased it. It's going around. In our case, you want to imagine it going around in a circle with uniform circular motion. So this is a phasor. It's going with frequency omega naught. Now I said frequency, didn't I? Of course, I really meant angular frequency, the number of radians. Omega naught is radians per second, not cycles. But everybody does this. When they say frequency, they leave it up to you. Unless they want to be very clear, people say frequency meaning either F or omega. Right? And you'll get used to this. So this is going around some constant frequency, omega naught. And it's going, by convention, we take the rotation rate to be counterclockwise. So this is positive. It's going around at a constant rate. And what you want to notice here, first of all, the tip is going to be moving at uniform circular motion, like I talked about earlier. Constant speed, right? And what's the projection? Well, here's the angle. The angle in general, it could be omega naught t, but that's when if it starts off here at t is equal to 0. But at t is equal to 0, it can be anywhere, right? So here's the general form of what the angle is. So what's this right here? Simple trigonometry. It's this. Does that look familiar? This is solution. So what we've concluded here, and it's very simple, there's nothing complicated about it, is that simple harmonic motion is the projection of uniform circular motion. What about this projection? What's it? Well, you can see the trigonometry. This, at any instant of time, is going to be given by that, due to the trigonometry, right? Simple trigonometry. Is that a solution? Oh yeah. You know, this cosine, like I told you, it can be a sine, it doesn't matter. These are equally valid as solutions. So projection either on the x-axis or the y-axis here is a solution. So why is this important? Well, it's important because, as I said before, and we're going to see it explicitly here, this uniform circular motion is a lot easier to handle than this oscillatory motion. And the way we handle it is not with phasors. They do it in optics, but people who do waves and oscillations, whether it's acoustics or any kind of waves and oscillations, the way we handle it is, we don't use this is a graphical or a geometrical approach here with this phasor, right? This is like the x-axis and this is the y-axis. What we do is, and it's much to our advantage, as you'll see, we look at it from an equivalent point of view, but this is the real axis and this is the imaginary axis. We go to the complex plane. So this arrow here gets replaced with a point that's going around a constant angular velocity in the complex plane. And at any point in time, it has a real part and an imaginary part. And either of those is a solution. Okay, so how do we see, the problem here is that for me to represent this point graphically or geometrically here, I've got to have an x value and a y value. It looks like I'm going to start using vectors. It's messy. But from a complex point of view, this point has a real part and it has an imaginary part. And I can represent it. Here's the real part, here's the imaginary part, and to represent the complex number I have to multiply by I, where I didn't write it down, but I is equal to the square root of -1, right? As you all know, right? Right? Okay. So you can see, there's no vectors here. This is how we can describe this motion here. We go to the complex plane, and we're doing it because it's easier to deal with uniform circular motion than it is with oscillatory motion. Now the next step here is to use this identity. This is true for any complex number. Does this look familiar to you guys?
Euler's.
Yeah, I think it's got Euler's name attached to it. This can be proved. There are different ways you can prove it. One way is with infinite series. You can write essentially a Taylor expansion, an infinite series. This has an infinite series representation, so does this, so does this. When you add these two together, you see that it's identical to that. Anyway, however you want to look at it, this allows us to rewrite this a simpler way. You can see here, factor out the A if you like. You can see that we have e to the I omega naught t plus phi. So our x here is given by this. Incidentally, when we go complex, when people write it in different ways. Okay. One way to represent this, see, we started with this. That's our real variable. That's doing this, right? Now we've gone to this complex variable that's actually doing something very different. It's going in a circle. So we should denote it differently, right? So some people use an underscore. In books, and in particular KFCS, it's emboldened. So this becomes bold. An emboldened symbol means that it's complex. Because we really do need to call it something different. Because this is, like I said, this is doing this. The complex, is doing this. Now, having said that, many people, when they write on a board or homework or quiz, it's just understood. This is the complex algebra, complex arithmetic here is used so much that it's just understood that we've gone complex here. And it usually causes no trouble. The fact that we don't specifically denote it, we just call it X. I can tell you don't believe me, but you will. After you do this, we're going to use it so much. So anyway, here's our solution. Technically, this is the complex displacement, right? Because it's doing this, not this. And we can make it even simpler because e to a plus b is equal to, here it is. Right? It's nice and easy here. It's because we've gone to this uniform circular motion rather than this sinusoids. So we can lump this, where is it? We can lump this e to the I phi into the a here, and we can write it like this. And now we have a complex amplitude. The complex amplitude is the actual amplitude with this phase factor here. So I think what I need to do at this point before we go on is tell you what where we're headed, the whole idea here. The idea is we don't solve, what we're going to be doing is not solving a real equation. We're going to solve the complex equation. And it's going to be much easier using the complex plane. And when we're done, we just take the real part. That's the bottom line here. And I know it may not sound like a big deal, but it turns out it's extremely convenient. It's really messy. And we'll see some of that as we go on. I don't agree with this anymore. I think we should, let me make some brief statements about this. We know that we have two different forms way back here. We knew yesterday that we have two possible solutions, right? We can see this, and they're equivalent. We've shown that. We can see it pretty easily from the complex point of view. So let me show you how you can do that. instead of our A, complex A being an amplitude times e to the I phi, we can write any complex number. You can always write any complex number as a real part plus I times an imaginary part. If we do that and go back to our complex displacement, here's what we get. If you do the multiplication here, remember I times I is minus 1. And look at the real part and the imaginary part. And then we find the solution as the real part of the complex displacement. We get this. So what this shows, this is one quick way of seeing that this is also an equally valid solution to our amplitude phase solution. Furthermore, we can get the connection between the two. Sometimes you want to know the connection between the complex approach quickly tells us what the connection between the two forms of the solution is. You see the triangle that we have here. So we recognize here in the complex plane, this is the real part of the complex amplitude. This is the imaginary part, right? So here's the real part. Here's the imaginary part. So the relationship between the two solutions, our amplitude phase solution and the sum of the two sinusoids here. This negative sign is not important here. It's all embodied in this diagram right here. And from this you can get the transformation between the two solutions. For example, if I know A1 and A2, right, I can tell you what the amplitude is. I get it by Pythagoras here. And similarly, if I know A1 and A2, I can get the phase. The phase has the tangent is A2 over A1. We derived this earlier. Look familiar to you. Remember we took the squares? We derived it. And similarly, you can show this. This is the inverse transformation. So it all falls out pretty easily from the complex point of view. Okay, so again, here's the idea. Here's what we're going to do. Let me say it again. We're going to be solving differential equations. We're going to be doing a lot of that. Quite common in science and engineering, right, and mathematics. And we're dealing with real phenomena here, real variables ultimately, but it's greatly to our advantage to go complex and solve that, as you will see. So we simply take our original differential equation, here it is, okay, and we let it become complex. We let it become complex. We then solve it, and you can see how easy this is. Can you see that this is the solution to that? You can see it. Why is it so easy? Because when you differentiate an exponential, you get it back. When you differentiate a sine, you get a cosine. That causes all kinds of trouble. And you might say, well, it's not that much trouble. Right now, it's not that much trouble. Once we put in drive and dissipation, it becomes a big problem. It gets more complicated. We really want to use the complex method when we generalize our model. So right now, if you just look at this, you'll see, oh yeah, that's a solution. Because when I substitute this into here, I take two time derivatives. That's going to, by the chain rule, I'm going to get a minus omega naught squared, and that's going to and it solves the equation. So this is called the complex, we'll call this the complex exponential method. We handle everything with complex numbers. We make our differential equations complex, our solution complex. We solve, and then we take the real part at the end. And here's just some of the advantages of exponential rather than trigonometric functions. See how I already wrote this down. This already happened. This is very simple. When you want to resolve, or I don't know what the word would be here, but here's the product of cosines. Here's an identity, a trigonometric. Some of you remember this is a trigonometric identity. The important thing here, and I should have written it, is the fact when you differentiate an exponential, you get the exponential back. Right? When you differentiate a sine, you get a cosine, and vice versa. So I know it seems really simple, but The analysis is going to get more complicated, as I said, and it's really advantageous to use complex numbers. And after a while, you won't think about this anymore. Okay, do we have any questions? Well, the complex method here, complex analysis method, has other advantages too. Remember this phase? What was it, way back? Remember this? And of course, I regret, you know, long ago, or whenever I did this, one of the times I taught this course, you know, why didn't I get yellow out instead of, why did I use white out, right? I should have used yellow out. Do you guys know what that is? Maybe you don't use it anymore. You know what white out is, right? Okay. Yeah, I should have used yellow out. Screwed up. But putting that aside, this is kind of complicated, isn't it? It looks kind of complicated. And I noticed that a lot of you had, well, you had trouble with the phase here. Most people think, oh, because this is to the right of their position is to the right of velocity, it's ahead in phase. No, no, as time goes on, you hit this first. So the velocity's in phase. Well, there's an easier way of seeing this. And I stupidly did it with phasors here. But this is identical. You want to think complex plane, okay? So I guess I did it for visualization purposes here. I'm thinking of this as a phasor. But it's equivalent to just taking this to be a point and making this the complex plane. Okay? They're equivalent. So here's x, and it's going in, for our oscillator, it's going in uniform circular motion here, right? Which is a lot simpler than this. Where's the, well, you can see where I put why is the velocity there? Well, here's x performing uniform circular motion in the complex plane there. I take the time derivative, brings down an I omega. Now, I can re-express I. The imaginary unit okay, and how do I know that? Different ways of seeing it. Remember, this is the cosine of pi over 2 plus I times the sine by Euler relationship or whatever. What's the cosine of pi over 2?
0.
Thank you. What's the sine of pi over 2?
1.
So, yeah. I know this looks strange. I'll never forget the first time I saw this as an undergraduate. It just blew me away. I was going to say something I shouldn't say, so I'm not going to say it. Yeah, this looks strange. So if you think this looks strange, you're in good company, I think. There are a lot of people who think it's strange, but it's clearly true, right? So the reason we do that here is because now we can compare. These are just positive. These are just essentially the same number. We can forget this. You now see the phase difference here. You can see that the velocity is not in phase with the position. Is it ahead or behind? Pi over 2 is 90 degrees, right? Remember? So is it ahead or behind? Well, see at time t is equal to 0, we have this is a positive number. So the velocity is ahead by 90 degrees, as I told you before, but this is a little more complicated before. But here you can clearly see it's ahead in phase. There it is. It's always ahead by pi over 2, which is 90 degrees. So we can represent it graphically here. We use this arrow or point. This x is going around like this. These are rigidly attached here, and they're going like that. The velocity is 90 degrees ahead in phase. And what about the acceleration? The acceleration is 180 degrees out of phase. It's totally out of phase with the position. So it can be represented by just an arrow going directly the opposite direction. And again, all these arrows are like they're rigidly attached and they're going around in the plane at constant angle, constant frequency. So this is equivalent to those graphs, but it's easier to think of it this way, isn't it? In those time graphs. It's yet one more advantage of the exponential of the complex method approach or phasor approach. Okay, so tomorrow we're going to spend a whole lecture on the experiment 1, right? And the reason for that is to give you some general experimental methods that people use when they do experiments. You know, like error analysis. We're going to do error analysis, as Young knows. Right? I'll try not to make it too big of a thing, but you need to, if you're going to be a scientist or an engineer, you need to know some error analysis. You really do. Okay, quantitative error analysis. So that's part of the lab, is to deal with error analysis. Okay.